Okay, so this video is going to be the final installment for our video lectures on first semester, and we've covered the nerves, we've gone over the brain, and the last section that we need to talk about is going to go over the spinal cord. So you should have your packet that talks about the spinal cord, and we'll run through those 10 slides. Take notes as you would when you watch the videos, and then the last day that we meet for your final exam, if you would bring those notes with you. So if you do those on the packet, bring the packet back with you. If you do them in another format, on a separate sheet of paper, whatever that looks like for you, go ahead and bring that with you. Make sure that you have it with you during the last class. Okay. So looking at the spinal cord is basically the connection between your brain and all the nerves that you guys have within your body. So this is going to extend down the vertebral column, and your nerves, your peripheral nerves that go out to your arms, your legs, all the way down to your fingertips and your toes, are going to extend off of that spinal cord. And so as information comes into those nerves, it will travel from those nerves to the spinal cord. The spinal cord will relay it to the brain. Once the brain figures out how to respond to that information, it will then send that back down the spinal cord, and the spinal cord will redirect it back out to those peripheral nerves so that whatever action has been determined will be carried out. Now, with the spinal cord, a couple of things. It is surrounded by those vertebrae, so it is very well protected. But in that protection, if you look at the vertebrae that are surrounding it, you'll notice that there are the projections off of those vertebrae. Especially off the backside, you have a process that comes off of most of your vertebrae, and the reason for that process is if you lean backwards, they will lay over the top of each other and prevent you from bending to a point where you would snap your back, or do damage to the spinal cord. Now, with those bone formations, even though they are designed to protect, if you do damage to those bones, they are so irregularly shaped that breaking them basically it makes them very sharp and they turn into little knives. And that's why anytime that you have an injury to the back, if you don't have to move the person, you don't want to, because you don't know if you've damaged any of those bones and could potentially be taking a very sharp edged broken bone and cutting through the spinal cord with it. So that is one of the reasons why they will try not to move somebody until they have them secured, if they suspect that there is a back injury. Now, the spinal cord itself is about the consistency of cooked spaghetti. So if you've ever made spaghetti and done the fork test where you take a fork and cut it to see how easily it cuts to determine whether or not it's fully cooked, that is going to be about the resistance that your spinal cord would provide as well. It is not something that is extremely strong. It does have a variety of protective measures around it, but the spinal cord itself is pretty delicate, and that's why you have to be very careful when you're dealing with the spinal cord itself. So, spinal cord is going to extend down that vertebral column, and as you make your way from the brain into the midbrain and then the spinal cord itself, when you get down into the lumbar section of the vertebral column, so remember, you had 7 cervical vertebrae, you have 12 thoracic vertebrae, and then you have the 5 lumbars. When you get down into that lumbar section, that's really where the spinal cord is going to start to change its form. And you have a couple of important features in looking at the spinal cord itself. So if you look at that picture that you have there, it talks about the foramen magnum. That's going to be the hole that you have within the skull that's going to allow for that spinal cord to pass out of the skull and make its way down to the vertebral column. Just below that, you have the cervical enlargement. And if you look a couple down, you'll see that there's a lumbar enlargement. That's actually where the size of the spinal cord is going to expand a little bit. And the reason that you see the spinal cord thicken at that point is because that is where you're going to have a massive number of nerves that are going to extend off of the spinal cord and go out to all the parts of the body. So that cervical enlargement, that is where most of the nerves are going to extend off that would serve your neck, your chest, and then go down into the arms. So because of the high number of places that it takes care of, a little bit thicker there just to accommodate that. Likewise with the lumbar enlargement, the reason that we see a thickening of the spinal cord there is because this is where most of the nerves that are going to extend down your legs and then go all the way down to your toes would come from. And so just because of that added number of nerves that are going to come off of that section, you see that part a little bit larger than the rest. Majority of your spinal cord, if you guys look at your pinky finger, that is going to be about the size, the average size of your spinal cord throughout the rest of that space. A couple of other things looking at that, if you look at the cauda equina, which is the very last term that you have on that list there on the A side, that actually translates to horse's tail. And the reason that it gets that name is because by that point in time, you no longer have the spinal cord in its original form. The spinal cord has actually now frayed and has become individual strands or bundles and takes on the appearance of the horse's tail. And so that is where that name actually comes from. If you look at picture B, or the B side, gives you a little bit different look at the spinal cord because here you have the spinal cord itself without the protection of the bone. So you are seeing what the true spinal cord itself looks like. You can see that brainstem, you get to see the cervical enlargement, the lumbar enlargement, and then you have a different term here that we haven't talked about, which is the filum terminale. And that is where the spinal cord is actually going to start to narrow. So you can see very easily there that you have a transition and it becomes more narrow and then becomes a very fine bundle of nervous tissue when you get to that end piece. And that's really where we start to see that spinal cord taper down as it comes to an end. If you look at the next slide, it talks about the Meninge layers. And I introduced this a little bit in our last class when we were talking because it does cover the brain as well as the spinal cord. And so it's a continuous layer of connective tissue that is going to create somewhat of a barrier between the bone structure and then the spinal cord or the brain itself. These connective tissues are very thick, they're very durable, and they do a variety of things. So when you look at the three layers, you have the dura mater, you have the arachnoid mater, and then you have the pia mater. Now the dura mater is the outermost layer. So this is actually going to line the inside of the bone structure. So the Meninge layers that protect or cover the brain, the dura mater lines the inside of the skull. It touches the skull directly. And then in the spinal cord region, the dura mater would line the inside of the vertebrae of those bones. Then you have, I'm going to jump to the pia mater. The pia mater is the innermost layer, and this is actually going to cover the surface of the brain or the surface of the spinal cord directly. So if there is a groove or a formation in the brain or the spinal cord, the pia mater will actually follow it directly. So we talked about the sulcus and the fissures, those grooves or depressions that you would have in the brain. And the pia mater will actually dive down into those grooves and follows it exactly. In between those two, you have the arachnoid mater. And typically when we hear the term arachnoid, we think of spiders. And the reason that this particular layer gets the arachnoid name is because it does have the appearance of holes. So just like you would think of a spider web having those spaces between the threads of the web, this particular layer of meninge is going to have holes or openings in it. And the reason for that is because of the cerebral spinal fluid that you have circulating through this area. To make sure that that cerebral spinal fluid can move from the dura mater and the pia mater and go back and forth between those two, you have to have those holes or those openings in the arachnoid mater. So dura mater, outermost layer, lines the bone structure. Pia mater is the innermost layer, lines the actual nervous tissue, whether that is the brain or the spinal cord. And then the arachnoid mater is sandwiched in between with spaces in the structure of that layer so that the cerebral spinal fluid can flow back and forth between the two. Now with the meninge layers, One of the biggest things that they do is hold that cerebral spinal fluid in place so that it is always very close to the brain and the spinal cord. And it's also going to help hold those two structures in place. So it helps hold the brain a little bit so that it doesn't hit the sides of the skull. And likewise with the spinal cord, also helps to kind of anchor and hold it in place. Now, neither one of these two structures, the brain or the spinal cord, has a lot of extra room to maneuver, but they are in liquid environments, and so they are somewhat floating, so to speak. And even though there's not a lot of room, there is the possibility that these two structures with a lot of force could get slammed and hit the bone structures that are protecting them. So if you think of something like shaken baby syndrome, where somebody has picked up and physically shaken a child with a lot of force, that brain is actually going to start to shift and rock. And as it does that, it's going to slam into the front part of the skull and then bounce off and hit the back part of the skull, um, or side to side, depending on how the child is being shaken. And because of that, with that amount of force, the meninges can't hold the brain structure in place. But for the simple day-to-day movements that we do, it helps to anchor, hold it so that we don't run it into the front side or the back side of our skull. When you get to that point, you can do enough damage where you would rupture the blood vessels serving the brain and get bruises and do other structural damage. So the meninges hold that cerebral spinal fluid in place and then also work to anchor the brain and the spinal cord so that they don't hit into the bone structure around them. The next one talks about the cerebral spinal fluid, often abbreviated as CSF when you see it. And the cerebral spinal fluid has a very important job in making sure that the brain and the spinal cord are always getting the nutrition that they need, the nutrients, the ions, and that they are basically being cleaned. So this is the way that we bathe our brain and our spinal cord to make sure that debris, clutter, bacteria, anything else that could be potentially harmful are not allowed to build up around those structures. So this is a very interesting design that the body has in that it is going to constantly bring new CSF in to the structure and then also drain older CSF off. And so when you look at it, you have these structures that are known as the arachnoid villi. And villi we haven't talked a whole lot about. They come up again when we get into our digestive system. But villi are basically these structures that work like straws. And as liquid or other material passes over the villi, it will actually suck that material out. And so the arachnoid villi are going to be strategically placed within the brain and the spinal cord so that older CSF that is potentially carrying debris or other waste product is going to drain off into those villi and be removed from the brain and the spinal cord so that that waste product is not allowed to sit in that environment and potentially do harm to the brain or the spinal cord. So when we talk about the cerebral spinal fluid, it typically should be a fluid that you could see through. It does have a little bit of a tint to it, but you should be able to see through it. And if you are thinking that somebody has an illness such as meningitis, one of the things that they will do is they will draw out some of that cerebral spinal fluid. And what they're looking for is, can they still see through that fluid, or does it have a cloudy appearance? Cloudy appearance is going to indicate that you have some sort of infection, typically meningitis, and if they can still see through it, then they know that there's not infection that is impacting that cerebral spinal fluid. As I mentioned last class again, you're typically looking at roughly around 120 mils of fluid that is going to take care of both the brain and the spinal cord. So the 4 ventricles that we talked about in the brain and then down through the spinal cord, 120 mils of fluid that is going to take care of that. And sometimes if we have the time and the availability, I will actually have you guys measure out what 120 mils looks like, because that's hard. I can tell you it's not a huge amount, but most of us don't think in milliliters. So when I say 120 milliliters, that doesn't mean a whole lot to most people. So considering that they are taking care of, or this fluid is taking care of the brain and the spinal cord, 120 mils is not a huge amount for how big of a job it actually is. The next picture I want you guys to look at talks about the parts of the spinal cord. And so what we have on this one, instead of looking at a side view of the spinal cord from top to bottom, we've now cut through the spinal cord and you are kind of looking down on that cross section of the spinal cord. So just imagine that the spinal cord was cut and you're now looking down on top of that. Couple of things that I want you to notice right off the bat is the arrangement of the white matter and the gray matter. So we talked about the difference between white matter and gray matter. If you are talking white matter, that's going to tell you that it is a nerve that has myelin protecting it. So it has that fatty covering that allows it to work at a slightly faster pace. Gray matter is going to be those nerve cells that don't have myelin. So they still work extremely fast, just not as fast as the white matter is able to. So white matter has myelin, works faster. Gray matter lacks myelin, works just a touch slower. So when you look at the arrangement of the spinal cord, you'll notice that the white matter is on the outside and the gray matter is on the inside, which is the exact reverse of the brain. The brain, if you guys were to remove the skull and take a look at it directly, you would notice that the gray matter is the first thing that you see, and you would have to get to the core of the brain in order to be able to see that white matter. So it's a little bit different in the arrangement. Some of the other things that you will notice when you look at the image of the spinal cord is you have two different ways to refer to the bundles within the white matter and the gray matter. So if you look for anything that is termed with the horn name, so you have the posterior horn that is top center, and it's a bracket that is surrounding the gray portion of the spinal cord. And then you also have the anterior horn, and that is just below that on the bottom side. And it's a bracket again around that gray matter. So when you talk about the horns, you are talking about bundles of that gray matter in the spinal cord. And then we add the directional terms like posterior or anterior just to let you know exactly what part of the gray matter that we are talking about. So horn should be connected to gray matter. On the other side of that, if you start looking around in the white matter, you'll notice a different term known as the funiculus. And you have a lateral funiculus, which is on the left, right about the middle. And you have the posterior funiculus, which is on the top right. And then you also have the anterior funiculus, which is on the bottom right. So this time, anytime we are referencing white matter, you are going to connect that to the term funiculus. And again, lateral, posterior, anterior is just going to indicate to you directionally where you're at within that white matter. Are you on the top? Are you on the back? Or are you to the side? The other things that we have here is you'll notice some of the other terms that we talked about with the brain. You'll see the posterior, you'll see the posterior median sulcus, which is the second one on the right. You also have the anterior median fissure that is at the bottom. Now, when you look at these two, you have sulcus and fissure, which we did talk about when we talked about the convolutions of the brain. So you had the high points of those convolutions, and then you have the low points of those convolutions. How deep those grooves go is going to determine whether or not you're using the term sulcus or you're using the term fissure. So sulcus and fissure is just a way to refer to a depression or a groove that you have within a structure and how deep it goes. The sulcus is shallow. It's not as deep. A fissure is going to be a deeper groove or depression that you would have. Now, the important thing that I want you to notice here, and this picture doesn't do a great job of indicating it, but you'll notice that there's a line. So where you have that posterior median sulcus, and then also where you have the anterior median fissure, there are lines there. And what it's actually trying to represent is the fact that you have a left and a right portion to the spinal cord. It is not one piece. There's actually two halves to it. And they are sandwiched very close together, so it's not like you see a space between them. But just like with the brain, we had the right and the left hemisphere. You also have that same structure with the spinal cord. So it's not severed, it's not cut all the way through, but you do have the fissure and the sulcus, which are going to almost divide it The only thing that holds it together is that structure that is known as the gray commissure. That's middle right on the slide. And you'll notice that little bracket just showing the narrow bridge of gray matter. So just a very small bundle of those nerves that are going to hold the two sides of the spinal cord together. So that's what the gray commissure is. It's a bundle of nerves that connect the left and the right side of your spinal cord. Otherwise, the fissure and the sulcus are going to divide those two parts. And at the very center of the gray commissure, you'll notice that you have the central canal. That central canal is going to be where your CSF would run through. So that is a hole or a space that is going to allow for that cerebral spinal fluid to be able to move through and bathe and take care of those structures again. So what we kind of talked about earlier, but now you can actually see that location of where that CSF would pass through that structure. The next slide that we have talks about the reflex circuit. And with the reflex circuit, reflexes are something that are innately built into your body. And when I say innately, all that indicates is it's not something that you have to learn how to do. It is something that is just automatically designed. You do it when the situation calls for it to be done. So it gives you the definition of a reflex. It says it's automatic and it's a subconscious response that you have to a particular type of stimuli. So what happens is the receptors in your body would pick up on a particular type of sensory information coming in. Sensory information always gets relayed to your central nervous system, which would either be the brain or the spinal cord. Remember, that depends on how high level the sensory information is. If it's low level, it gets directed to the spinal cord. Spinal cord takes care of it. If it's high level, it would go all the way to the brain, and the brain would have to deal with it. Once the brain or the spinal cord determines how to deal with that sensory information, now we're going to redirect that back out to your peripheral nerves, and it's going to be taken care of by an effector. Effectors are either going to be muscles or they're going to be an endocrine gland. So depending on the situation, you are either going to have hormones being dumped into your body to respond to the situation at hand, or you're going to have some type of muscle movement that is going to allow you to move in response to that. So something was thrown at your head, muscle movement is going to allow you to deflect it or duck, move out of the way. If you are in a scary situation, now you're probably going to resort to the hormones and have those hormones being dumped in your system and go into your fight or flight response. So those would be two examples of how your body would then react to that. Now, you have all sorts of reflexes that are innately designed into your body. And while you don't have to learn how to do them, some of them you actually can lose if you don't use them within a certain amount of time. So the sucking reflex for a newborn, that is something that they have a window of time after birth to utilize. And if they don't use it fast enough, they actually will have to then relearn how to do it. So within 24, 48 hours, if they have not used that sucking reflex, they actually will then have to be retaught. But otherwise, they have it right off the bat. As soon as they start nursing, then they use that reflex and it will work for them as long as they continue to use it. You have a startle reflex. If you have ever watched a newborn sleep or a very young child sleep, if they get startled while they're sleeping, they will actually throw their hands up above their head while they're sleeping. They don't necessarily wake up, but that is their startle reflex. And a lot of theories behind the startle reflex. One of the theories is that when a child is scared in their sleep, they actually kind of translate that to they are falling, and so they throw their hands up to make it easier for somebody to be able to catch them. There's no way to really tell that that is what's going on, but that is one of the leading theories behind why we have a startle reflex. Some of the other reflexes that you guys have, you have the knee jerk. You get hit in the knee in the right spot, you're going to kick that leg out in response to that. And so if you look at that spinal reflex, it shows you the same thing that you have on the reflex circuit. It just shows it to you in a little bit different way. So this time, instead of showing you receptor and central nervous system and effector and writing it out like that, they put pictures where those word boxes were. So shows you where the receptor would be, but now it shows you that receptor being part of your skin. You have some sort of sensory information coming into your skin. Now it shows that sensory information, follow the arrows, coming into the nerve. That nerve leads into your spinal cord, and now that information is being processed within your spinal cord. So if you find where the number 3 is, it talks about the inner neuron. Those are the nerve cells that you guys have in your brain and your spinal cord. They will process that sensory information coming in. And now if you follow the arrows, we see that that sensory information or that processed information is getting directed back out. Spinal cord has figured out how you are going to respond to that sensory information, and it sends the response out to your muscles. And now that muscle is going to contract, allowing you to move and carry out the response. So that reflex circuit slide and the parts of a spinal reflex, like I said, those two go hand in hand. One gives you the word description, and then the second one actually puts pictures to what's going on and how that would be carried out. The next two slides that we have talk about ascending tracks and descending tracks. And I am not worried whatsoever that you memorize the ascending and descending tracks. If you were going to go into this as a specialty, yes, you would probably need to know these. But for our purposes, the biggest thing that I need you to understand is how they work. So within the spinal cord, you have these two tracks, ascending and descending. And true to their name, if it's an ascending track, it takes information up. Now, ascending tracks, because they are going to the brain and the spinal cord, they are going to your central nervous system. The only type of information that they can carry is sensory information. Any sensory information that comes into the body always goes to the CNS. That's the only place it can go. So ascending tracks are going up to the brain and the spinal cord. Descending tracks are taking the information and they are now carrying that back out to your muscles or to your endocrine glands so the response can be carried out. So descending tracks, true to their name, always go down, but they are only carrying a motor response, whether that's going to your muscles or that is going to an endocrine gland to be carried out. So ascending tracks go up, descending tracks go down. Ascending deal with sensory and descending deal with motor response. The other thing that is important to understand is if I give you kind of a real life example to think of the ascending and the descending tracks as being elevators, but the elevator can only go one way. So an ascending track is a bundle of nervous system or nervous tissue that you have that is going to transport information up, but it can only carry information one way. So when the response is formed and starts to be sent out to the muscles or to the endocrine glands, it cannot use that same track. So an elevator taking that information up, but it's a one-way elevator. It can only transport things up. It cannot bring anything back down. So please make sure that you understand that with the ascending and the descending tracks as they are one way and one way only. So if you have an ascending track that takes up a particular spot within the spinal cord, then a descending track has to be somewhere else within the spinal cord to bring information back down. The last part that I want to talk about, and cranial nerves, spinal nerves, we already talked about that. I want you to skip over to the spinal nerves. The picture that you have here, I like certain things about it. I dislike certain things about it. The first thing, when you look at that picture, you can see the brain and the spinal cord. The little knobs that you kind of see in between the different spinal nerves are actually the vertebrae. So again, they cut this as a cross section, and you are looking at the cross section of what it would look like if you would cut that spinal cord down lengthwise. I wish they would run the nerves all the way down the arm and all the way down the leg so that you could see that. How this picture is set up, it looks like those nerves get to about the shoulder and quit, and get to the bottom of the glutes and quit, but they actually would run all the way down to the fingertips and all the way down to the toes. But it does give you a very good visual of the spinal cord running down those vertebrae. Like I said, you can see just a little bit of the vertebrae because they were cut away. And then how they have identified each one of those nerves. So you have C1 through C8 showing you all of the branches of nerves that would come off of that spinal cord and then extend out to the neck, the arms, the upper body. T1 through T12, again, these would extend out and go to the rib cage, wrap around to the front, take care of the chest, the pecs, all the other muscles of that core region. And then L1 through L5, which are going to take care of the lower back, and then down into the legs. And then you have the sacrum from S1 to S5 and the coccyx finishing it off. So kind of giving you an idea of how those spinal nerves are going to branch off of that spinal cord and extend out to all the parts of the body. Now, one thing that I mentioned earlier is that we have 7 cervical vertebrae. So C1 through C7, those are our cervicals. But you'll notice here that we have 8 cervical nerves. And the reason for that is on your top cervical vertebrae, you have a nerve that comes out on the top side and then on the bottom side. And that's why we see one more cervical nerve than we actually have cervical vertebrae, is because on that first one, you get one on the top and the bottom. And so you get one extra in that cervical set. For all the rest of them, it would be true to form. So your thoracics, you would have 12, your lumbars, you would have 5. So they follow suit. The other thing with this is it gives you a good understanding of what would happen if you would then cut your spinal cord at any point. So when we talk about spinal cord injuries, the higher it is on the spinal cord, the more loss of function you are going to have. Because wherever a spinal cord is cut or transected, unfortunately, the brain is not going to be able to get information past that point. So once you sever the spinal cord and cut it all the way through, the brain is not able to get information past that point. So if you look at that picture and you were to cut the spinal cord at C1, C2, anything below that point is now not going to get any information from the brain. If you move that down to T12, and that's where the spinal cord was cut, now anything above that, you would still have function because they are still going to be able to get information from the brain. Those nerves would still be able to get information from the brain, but anything below that T12 point is not going to get any information. And so you would lose function below that point. So it kind of gives you an idea of being able to see how those nerves extend off and exactly where they're going into the body. Ultimately, then, what parts of the body would no longer have information or sensation from the brain because of that particular injury. So that kind of wraps up the spinal cord. As I mentioned before, we could spend our entire semester on the nervous system. There are so many layers and topics and parts of this, but for our purposes, just getting a good understanding of the nerves, what they look like, the parts of the nerve, and then the major lobes and functions of the brain